that's not really another thing. I'm going to use O plus rather than cross here. It may, now, I wrote it here, so it probably is another thing, right? But how do we know it's a different thing from Z mod 4?
Because it's different from Z mod 2 squared.
Wait, say again?
It's different from Z mod 2 squared.
How do I know in terms of the group structure? I know that the theorem says that it's different, but just this is not cyclic. Everything in here has order at most 2. Everything in here when taken to the second power is 0. Okay? So this is cyclic, this isn't, so these are non-isomorphic groups of order 4. Okay, so my something of order 2 squared, are there any other possibilities? There's 4. Like I can take 2 squared and do that in one chunk, or I can split it into 2 distinct chunks. But I think that's all the choice I have, right? Like I can either have 2 2s, or I can have a 2 and a 2. What about the 5 cubed? That's a little bit more complicated. What's one possibility though? What? Z mod 125. That's one possibility. Okay, what would be another one? Okay, Z5 plus Z25. 5 times 25 would be 125. And that's not the same as Z125 because everything here has order at most 25. Is there anything else? Yeah, Z5, Z5, Z5. Is there anything else?
Z25 cross Z5.
Ah, Z25 cross Z5. Is that different from all the ones I have so far? It does look different, but is it non-isomorphic to the other ones?
I think it's isomorphic to Z5.
Yeah, it's going to be isomorphic to this.
Cross A, let A, B, let A, B.
Oh, okay.
And I can even tell you what the isomorphism would be, or one isomorphism.
Let A B equal B and B equal A.
Wait, say again?
Let A B equal B and B equal A.
Yeah, that's right, yeah. So phi of A comma B equals B comma A. That would do it. That would be an isomorphism. Okay, so I don't really need to add that to my list. That's maybe redundant to one of the other things on the list. Anything else? Like I can have 3 together, or I can move one of these over. So I'm trying to like make the finger movement smooth, but I haven't any practice. Okay, or I can have like 3 separate 5s, but I think those are the only options, right? All right. So how many possibilities do you think there are for a group of order, abelian group of order 500? Yeah, it's just picking off the Chinese restaurant menu at this point. You can have 2 appetizers and 3 entrees. Well, I can have 2 appetizers and 3 entrees. Really, I should say you have to choose between the 2 appetizers and choose between the 3 entrees. All right. So the possibilities for G, I'm not going to write them all down, but there's 6 of them. You choose this or this. I'll write down one of them. You choose this or this, and then you choose this, this, or this. So here's another one. Six in total. Okay. Either way, because we are doing a combination of something from column A and something from column B, everything here looks like it's a direct sum. It does, I mean, is it? Wait a second. No, I'm confused about something now. Because one abelian group of order 500, like what's our favorite abelian group of order 500? Z5. Is that on the list? No. If not, this is a hell of a lesson. Our theorem is wrong. No, it's actually on the list. Think again. I mean, it's not literally on the list, but it's isomorphic to something on the list.
Z mod 4, Z 125?
Yeah, that one. How do we know Z4 plus Z1? What?
It's cyclic because the factors are covariant.
Yeah, 4 and 125 are relatively prime. So this is isomorphic to Z mod 4 times 125, Z500. We have a theorem that says that if we have Z mod n plus Z mod n and the m and n are relatively prime, then the direct product is cyclic. So yes, Z mod 500 really is there, just in disguise here. Okay, so that's actually, that would be something that I could definitely see asking on the test. But you'll notice I'm saying could, not will. before we start the proof. Yeah, Angel.
That theorem that you just stated, is that an analytic thing, or which are the real?
Oh, the one about Z mod M cross Z mod M being cyclic. Oh, that's a good question. So we said, because the direction we used was if M and N are relatively prime, then the product is cyclic, right? We didn't say the converse. Is the converse true? So in other words, if Zm plus Zn is cyclic, then M and N have to be relatively prime. Did we do that?
Chapter 8, right?
Okay. Was that one of the things we did last time? I feel like we did something like this last time.
Oh, yeah, we did.
Yeah.
Yeah.
So both directions are true. Okay. Z mod M plus Z mod N is cyclic if and only if M and N are relatively prime. Because if they're not relatively prime, they're a common factor, and we're able to show that everybody's order can be bounded by something smaller than M times N. That'll be in the notes. Okay. It is also in chapter 8, by the way. You can find it there too. What other questions? Yeah, Sam.
What were we trying to do in this question? Were we just trying to write down what the direct sum of Z500 was in terms of prime abelian?
So what I'm claiming to have done here, that's always a good question. What the hell did you do? I have to tell you a quick story. So one time I was taking a graduate number theory class at A&M. I was an undergrad, but taking a graduate number theory course. It was taught by this very respected scholar named Paula Treptoff, who subsequently went crazy. Like, this was long after I was done at A&M. It happens to more mathematicians than you think. Anyway, she was teaching this. Right. So she was teaching this graduate seminar. She was actually a splendid teacher and a fantastic mathematician to boot. Okay. But she was talking about, and I don't remember what the topic of the lesson was because it was a lecture, and that's sort of how I interact with all lectures is my attention goes. But about 30 minutes in, she was on some topic that we knew wasn't going to be part of what we were assessed on or anything. And this dude named Dimitri, who was a grad student, just raised his hand and said, not to be rude, but where's all this going? And the way he said it sounded extremely rude, actually. Much more rude than Sam's question, which did not sound rude at all. Okay, and I don't remember what she said, but she seemed kind of taken aback. But that's graduate education for you.
Well, there's a theorem, if anybody starts with not to be, then the direct follow-up is going to be that. I think that's
okay. So what is it?
I don't mean it's extremely rude.
All right. So what is the thing we were trying to do here? So what I claim that we've just done is subject to knowing that this theorem is true, which there's still a lot of work to do there. We've now classified every abelian group of order 500. Done. There are 6 of them. Classified up to isomorphism, which is an important distinction to make. Okay, so there are 6 different non-isomorphic abelian groups of order 500. Now you may wonder how many non-abelian groups. That's a lot harder. We're not going to get to do that in this course. I can, if you want to learn more about how to do that, by the way, and this is a good chance for me to talk about how the following problem sets for this course are going to be structured, because we still got 3 or 4 of these left. Okay. So the way those are going to be structured is most of the problem set, like the mandatory stuff, is going to be the new material. So this week it'll be problems kind of like these, and maybe having you interpret part of the proof of this theorem. After this week, it'll be rings, so problems about rings. The additional problems will be opportunities for you to do one of several things. One is you can just keep doing problems from Gallian about the new material. That would be one possibility. Another possibility, if you're looking to increase your exam grades, is because we're going to have extra lives in about 3 or 4 weeks. I forget how many, like 4 weeks, I think. You can find learning objectives for which you haven't totally aced the exam questions. I've listed exercises from Gallian that are good for practicing those, and you can do those exercises. So for additional problems from now on, you can go back and do things that were earlier in the course in order to fine-tune things that you want to do extra lives on. I think that's a good option for a lot of you. If you don't feel the need to do that particularly, or you can mix and match these options, I am going to include a sequence of problems that leads up to a really nifty theorem about non-abelian groups, which is called Silo's theorem. Silo's theorem says, if I have a group of order 500, this is just an example, that's divisible by 5 cubed, and 5 cubed is the largest power of 5 by which 500 is divisible. Okay? Silo's theorem says there has to be a subgroup of order 125. Okay, so one thing that Charles mentioned a long time ago is Lagrange's theorem says that if I have a subgroup of a group of finite order, the subgroup order has to divide the order of the group, right? We all know this by now. You showed that you know it on the test, okay? But what isn't necessarily true is that the group has to have a subgroup of every possible divisor order. That is not always the case. A4, for example, does not have a subgroup of order 6, and A4 has order 12. Okay, but Seal's theorem says sometimes you can guarantee there will be a subgroup of a certain order. And that is one of those cases is if you're looking at the largest prime power divisor of the group order for any prime to divide the group order. So 5 cubed would be the order of a subgroup 7 over 4. Okay, and in fact, the Seal theorems let you count how many of those there are. Well, not exactly, but in a lot of cases you can, and even when you can't, you can say something about how many there are, and it's wickedly non-intuitive. And the Seal theorems are used to at least make progress towards classifying non-abelian groups of a given order. Okay, so that's where all that is going. And if you want to learn more about how to do that, so the problems about semi-direct products in the old problem sets, that's a good thing to do. And the Seal theorem problems are a good thing to do. And if you make some headway with those, then I can tell you the rest of the story about how, given an order like 77, we can actually classify all the groups over 77, not just the abelian ones. Okay, but I think that should be optional course material at this point. It's pretty hard stuff. Not that it's beyond any of you. It's just, you know, we've made you learn so much already this semester. We thought you shouldn't have to learn all of group theory in one semester. But if you want to learn all of group theory, or at least all of finite group theory, you're not so far away actually. Like there's more that you can do, but I can show you where to go to do some of it. All right. So anyway, about today's lesson. We're going to do the proof of a hard theorem. This will probably be the hardest proof of the entire course today, because after this, we're off of that plateau I was showing you in the diagram earlier, and we're back onto like basics of rings, and then we start building the structure up again. So today is the plateau, or the peak, okay? Which means I should tell you a little bit about how I think you might want to enjoy today's class, all right? Because today is going to be mostly me performing things and probably making a lot of mistakes. The entire proof I'm going to do is in Gallien's book. And I don't mean like I'm going to do my spin on it. It's pretty much Gallien's proof. If anything, I'm adding a few details just to improve understandability, I hope. Okay. So if you don't want to take notes today, you don't need to. If you want to, because that's a good way for you to engage with what we're doing, that's fine. I won't be offended either way. But I'd kind of like for y'all to just follow along, make sense of what we're doing as we go along, and feel very free, freer than usual, to ask questions. And that means like interrupt and ask questions if you want to. Because there are going to be some steps that are not going to be totally, like usually when I write a proof, the steps are like pretty much based on things we've done recently. And I'll be like, why is this true? And someone will say, you know, because blah, blah, blah. And this time around, I'm probably going to not do that all the time. So I want you to feel free to raise your hand and, you know, be an interactive listener and say, wait a minute, why? Okay? And then we'll talk about it. And we'll do as much as we can today, and then the rest I will relegate to the vlogs, all right? Because I want you to experience the whole proof. One thing I might do on the final exam is ask you to just write a half a page to a page about what you understood of this proof. And it will not be the entire proof unless you can master a whole lot of material, because there's a lot of little tricks that Gallien does to prove this theorem. But I'd like for you to understand the general strategy and some of the ideas that are used. This uses a lot of what we've learned over the last 10 weeks. Okay, sound good? All right, let's get to work.
First question?
Yeah.
What name? What are you going to call this one?
This theorem, it is called, yeah, I feel like, I feel a little bit bereft because this theorem doesn't have somebody's name on it. Maybe it could be Engelbart's theorem. Nobody else has claimed it. And I actually don't know who first published a proof of the theorem. I think this is one for which there's probably several proofs out there because it links up with a very similar theorem about modules, a very similar theorem about vector spaces. So that's probably part of why nobody has their name on it, is it's one of a family of theorems in abstract algebra. But what we're going to call it is the classification of finite abelian groups. Yeah, you may call it the fundamental theorem of finite. I use the term fundamental theorem very sparingly because a lot of the time that phrase gets abused. Take the fundamental theorem of algebra, for example, which says that any polynomial with complex coefficients has a complex root. Okay, that is a fundamental theorem. if you think fundamental means important. But in terms of the proof, there's nothing fundamental about that. And the proof isn't even algebra, it's topology. It may be complex analysis. So I'm a little wary of fundamental theorem, this or that. I call it classification because to classify in mathematics means you say, any object of this type has to be one of the following things. Like 500, any finite abelian group of order 500 has to be one of these 6 things, or isomorphic to it. So we're classifying. All right, so here's the proof of step 1. Okay, and both steps 1 and 2 are pretty major to-dos. Okay, so step 1. First thing I need to do is I need to remind you of something. And I'm not sure it's a reminder for absolutely everybody, it depends on which additional problem you chose, but I can remind you of why it's true pretty quickly. If G is abelian, phi from G to itself, defined by phi of x equals x to the, and then I need an integer name, let's call it k. Okay, so fix any positive integer k, really any integer k would be fine, it doesn't need to be positive. Fix any integer k, this function, phi of x equals x to the k, is a homomorphism, if G is abelian. The abelian part is really important here. Okay, here's a brief sketch of why it's a homomorphism. Okay, so to show it's a homomorphism, show phi of xy equals phi of x times phi of y, right? All right, well, what's phi of xy?
xy to the k.
It's xy to the k. Okay, but if we're in abelian land,
We can distribute.
X to the k, y to the
we
k.
move all the x's and y's around. I mean, literally written, this is xy, 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 however many xy's you have. But in abelian land, you can gather up all the y's, all the x's. That's the same thing.
Separate them. X to
X to the k, y to the k, which is the same as phi of x, phi of y. That's why that works. It's totally untrue if we're in a non-abelian group, but that's not where we are today. Okay, so that's homomorphism. The reason I want to point that out is it helps us to prove the first step of this thing here, which is by writing this down and saying G is the internal direct product of these, I'm surreptitiously suggesting that these are subgroups of G, without saying it out loud, but they are subgroups of G. Okay, so let's assume G is abelian of order p to the a times m. A is greater than or equal to 1. Oh, sorry, I forgot to write one thing here. P does not divide m. Really crucial there. Okay. And define h and k as I did over there. Okay, that's all the column left means.
So this P is a prime, right? Or is it
Yeah, P is a prime. Sorry, after a while, anytime you say P, we mean prime. Okay. Yeah, so P is a prime. And see, that is a good example of something that everybody should be doing, is interrupt me anytime I say something that doesn't make sense, it doesn't make explicit what I should.
A is greater than or equal to 1?
A is greater. In other words, I don't want P to be in there for stupid reasons. Like, oh, technically that's 3 to the 0 times, 17. Well, I don't care if it's 3 to the 0 times something. Okay. There has to be a factor P in there. All right, so that's our assumption. All right, then. H and K are subgroups. And I claim that we can say that they're subgroups because of what we did here. And I'm wondering if anybody sees why. Because if I define that homomorphism then I can think of these in terms of the homomorphism.
K is just equal to P to the A or M.
Say again?
K is just equal to H or PA or M.
Well, K is going to be, oh, you mean which K? This K or this K? K's are group elements.
That
Okay, the K's are group elements. It's not going to be integers necessarily. H and K are subgroups because they are kernels of these types of homomorphisms. So in other words, I just said this is a homomorphism. Now, suppose K is P to the A, all right? So that I'm calling that the P to the A power map. It takes everything to its P to the A power, all right? Well, which things go to 1? That's the kernel of that map. Okay, the kernel is just set of all group elements whose P to the A power is the identity. Okay, the kernel of the nth power map is the set of all group elements whose nth power is the identity. Okay, so those are subgroups. In fact, they're normal subgroups. How do we know they're not subgroups but normal?
Kernel is always normal.
Oh, that's a good answer. That's a better answer than what I was thinking of. What's the other answer?
subgroup of abelian.
Yeah, we're in abelian groups. Everything's normal. Yeah, either answer is a good answer. Okay, just in case we need it. Well, in fact, we do need it because we're gonna show that G is a internal direct product of H and K. Part of what we need is that H and K be normal. So let's write that down. So H and K are normal, which is one of the things I need. It's one of the components I need to show that G is an internal direct product of H and K. Does anyone remember what the other two components are?
They intersect at the identity.
They intersect trivially, right? And what's the other one?
It's the whole group.
Yeah. Yeah, joining H and K gives you the whole group. In other words, H times K is the entire group. Okay. I think I'm going to show the trivial intersection one first. Okay. Let's suppose. Well, first of all, does the identity have to be an H intersect K? Yeah, the identity, I mean, two reasons really. One of them is each of them is a subgroup, so each contains the identity. The other reason is the identity to any power of the identity, so of course the identity will be in both H and K. Okay, so I'm going to leave that part off. But let's suppose that X belongs to H intersect K. All right? So then let's write down what that means about X, because we have definitions of H and K over there. So that means X to the P to the A is the identity, and also means X to the M is the identity. Okay, now I'm going to ask you for a little input here. The input I want from you is, what does that tell us about the power, the order of X? Yeah. The order's got to divide both P to the A and M. Okay, so I'm going to write that down. While I'm writing that down, you think about which numbers that could be.
How does that interact with the fact that P does not divide M?
Whoa.
There you go. Yes. The answer is yes.
What's the only number that can divide P and M?
Okay. Yeah. The order of X has to divide both P to the A and M, and we already said P doesn't divide M. So 1. Right. So 1 has to be the order of X. Since P to the A doesn't, or let's just say P doesn't divide M, that means that the GCD of P to the A and M is equal to 1. And order of x is a common divisor of p to the a and m. So that order of x has to be 1. And what does that mean about x? So x is the identity. Notice I'm using like a stylized one for the group element, the identity, and like a regular one for the number. Okay? So x has to be the identity, and that proves that the intersection is trivial. Cool. All right, next part's a little bit trickier. All right, so to show, all right, so we're going to show that HK gives us the entire group. All right, remember this means, just as a reminder, HK is defined to be the set of all products H times K, where H comes from the subgroup H, and K comes from the subgroup K. Okay, so this is showing that every element of G is obtainable as something from H times something from K. Which is crazy when you think about it. That's just nuts. All right. So now we're going to have to use a little bit of number theory. So I think here's what we're going to do. I know that HK is a subset of G. HK is a subset of G because everything that's something from H times something from K, well, those are both subgroups of G. So I'm definitely multiplying two things that are elements of G, so their product will be in G. So the fact that this is a subset of this is not in dispute. We know this is a subset of G since H and K are both subgroups of G. Okay, it's the other direction we need to worry about. So let's assume that X belongs to G.
Can't we say that HK is a normal subgroup of G?
Let's see, what do we know? We know that H and K are both, yeah, no, okay. Can you justify that? I think you're right, but I want to see if you can prove it.
Well, we would need to show the subgroup.
What we're doing is a subgroup. There's something in one of the internal direct product videos, I think, that I said. H and K are both normal. If they're both normal, the product will be a subgroup. And it's normal because, as Paul said, it's abelian. We're abelian. All subgroups are normal. So I could actually put less than or equal to sign if I wanted to. Same here. Okay. So you're right. I wasn't going to use that here.
But because it's a subgroup of an abelian group, it would have to be normal itself, right?
Exactly. Right. Yeah. All right. So let's assume X belongs to G. All right. Then one thing I know that this is true. I'm trying to remember if that was what I wanted or not. Show every X in G is in H times K. Okay. I may need to, does anyone have the book with them? Yes. I may need to consult the book. Okay.
Sure, you get the right patient.
Okay, thanks. Yeah, there's this one step. I had it yesterday when I was taking the dog to daycare, and then I'm like, what makes me feel that? It escapes me.
X equals X to the first, and then you see even one.
Okay.
If we separate it out, can't we show that X is a number of K, and then we can use that down?
Oh, that's, yeah, okay, that's clever. Right, okay, thanks. You mind if I just keep this up here? Yeah. I was trying to remember what they were, because they're doing this trick in the first power, and I was trying to figure out what it was they were doing in the first power. It was actually this thing. So I actually don't think I need this step at all. So here's the deal. We want to show X some h and h and some k belonging to capital K. There we go. Okay, so the trick is, we're going to write 1 in an incredibly creative and annoying way.
Going back to the earlier with the 1 is equal to x times p to the a plus y times m.
Yes, we're gonna write 1 as a linear combination.
Linear combination
of p to the a and m. Okay, so since the GCD of p to the a and m is 1, we know that this number 1 here can be expressed as a linear combo of p to the a and m. For some integers x and y. There we go. Okay. I could have probably figured that out given about 3 to 5 more minutes at least if my ride with Rosie the other day at Lucy's was any evidence, but I didn't want to waste your time. Okay.
Something other than x then?
What?
Sorry.
Oh yeah, thank you. That would be bad. Let's use would y and z be okay? Yeah, it's just Josh has pointed out that the symbol x is already in use. Thanks. Okay. So that's the rule that says pay, which is what I like getting every month. Okay, so now what? Why did we do that? Well, here's why. Okay, so I know x to the first is the same as x to the p to the ay plus m. And I'm actually going to take that and switch it around because I think it's more useful to have it this way. X to the mz times x to the p to the ay. Okay, now why would I do such a thing? Well, I claim this belongs to h and this belongs to k. Because h is the set of things, the p to the 8th power of which is the identity. So it's x to the p to the a m v. And I probably shouldn't have erased that other step I had earlier. That was actually kind of useful to have around. What is this? That's the identity. It's the identity because